Bismillahirrahmanirrahim. So we will continue with the topics we were discussing last time. These days, actually, the amount of material that exists, thousands of lectures and thousands of courses, is so much that it is not possible to teach the students the substance. So all you can do is teach students how to learn, and that is very crucial. If the students learn how to learn, then everything is available now on the internet, which it wasn't in the past. So this is a great blessing today that you have that. In the olden times, Imam Bukhari had to travel from one city to another in search of knowledge. Today you can get everything on your mobile, but you have to have the desire to learn and also the understanding of how to learn. And especially when it comes to MPhil and PhD, 90% of your thesis will be based on material that you have to learn yourself. Nobody will teach it to you in any course, because the coursework material is not ever research material. So I am focusing on some basic principles which are useful everywhere. Mathematics by itself is something, you see, it's a separate reality from the real world. This is something which is not well understood even now in the West. This is something that the philosophy of mathematics, which was discussed very clearly by Umar Khayyam, those are the people who understood mathematics, the older tradition. But in the West, for reasons which I cannot explain now, I have discussed these elsewhere, the whole concept of mathematics was misunderstood. And this is actually, Raju has made the most detailed study of this in a number of articles. So if you want to understand why the West misunderstood mathematics and continues to do so, I mean, it's not that this is a problem which has been fixed, it remains. So I am teaching you some abstract mathematics. At the moment it doesn't seem like it has relevance, but it will appear. I am faced with a dilemma in the sense that it is possible to bypass a lot of mathematics and teach you the practical macro results. It's basically the issue of how much do you need to know about the engine of the car. I can teach you driving without teaching anything about the engine, and but it helps to know something about the engine. So currently the courses are structured to give you a lot of knowledge, much more than necessary, about the engine and very little about driving. So I am trying to shift the balance so that there is less knowledge about the engine and more about driving. But still, I think it's not a good idea to completely omit the knowledge, the theoretical knowledge that you need. So I'm focusing on sort of a minimum necessary subset. So understanding polynomials, curves and graphs, this is very important to be able to build mathematical models. Currently, the students that we graduate all over Pakistan, they have no ability to build mathematical models. Now with this background that I am trying to teach you, you will be able to build mathematical models, inshallah. So we start with dua. Allahumma akhrijni min al-dhulumat al-wahmi wa akrimni bi nur al-fahmi. Allahumma aftah alayna rahmatik abwab rahmatika وانشر علينا خزائن علومك برحمتك يا أرحم الراحمين. So one very important aspect of this dua is that we understand that ilm is a real treasure, because unless you value learning, you will not be able to put in the effort. It's the treasures that exist require work to get. So if you don't value it, then you will not put in the work that is required. So, and also struggle is required, and sometimes, I mean, as it is said that if you fail to understand, then you have to work harder to understand. And one of the things is that because you have been subjected to a very bad methodology of education, you have been given material to learn which it was impossible for you to learn at the level of understanding that you had. So it is very possible that you started out with this attitude that I am trying to tell you, that you should make an effort, and you made an effort and an effort and an effort, and ultimately it all failed, and then you decided that it doesn't work, so there is no need to try. If I can't understand something in 2 or 3 times, then it is beyond my capability. So now what I am trying to teach you is all stuff that is possible to achieve, even if you may fail to understand it for 5 or 6 or 10 times, then you will succeed on the 11th time, because this material is not so difficult that you cannot succeed. Now if I was to try to teach you advanced relativity theory, then no matter how much you tried, you would not succeed in learning it, because you don't have all of the things, all of the pieces that you need. Every piece of learning is simple. It's just like taking one step and a second step. But if you are asked to make a jump of 100 feet and you're not given the intermediate steps, then you cannot do it, and ultimately you realize it's impossible because you don't have all of the pieces. But here I am constructing a path in which all of the pieces are present, so there is no so this is something that you need, because your past experience is not good in learning. So but there is always a risk in learning, that you try and you fail, and then you say, oh, I'm not capable, and then so you have to work hard and hope, and then ask. There are many people around. That is, if you fail to understand something and you try very hard and you still fail, then you should ask somebody, because this material is not impossible to learn. That's the important thing. And you have been given in the past a lot of material which is impossible to learn, and you have just memorized it. So we remember that seeking knowledge is the highest form of worship. You make the intention to acquire knowledge only for serving others. This is how you should live your life. Not because this is exactly the opposite of what is being taught to everybody, that everybody is greedy, everybody is selfish. All we want is to have our own advantage. We don't want to give anything to others. So actually this way of living is very harmful to us, because people who are concerned with themselves, their hearts become sealed to feeling the pain of others, because they do things which are selfish and they hurt others, and then they have to the heart has the capability to sense the pain of others. But if you are going to harm others, then you cannot afford to feel that, so your heart becomes sealed. But now then there is a paradox. When your heart becomes sealed to the feeling of others, it also becomes sealed to your own feelings, so you can never feel happy. So it's a very strange phenomena. So this sort of utility maximization actually leads to utility minimization, because it becomes impossible for you to feel happy. You can have all the riches of the world and you will not feel happy, because your heart has lost the ability to feel. So we start by this picture, which exists in Umar Khayyam's book in 1100 yani CE, 4th century Hijri. He is describing how to solve a cubic equation, and he also said something very interesting and important, that cubic equations cannot be solved by ruler and compass methods. A proof of this impossibility was given in Europe 750 years after Khayyam. They learned this thing 750 years later. And his book, which laid down the principles of algebra, was transmitted. You see, this is something that they conceal. They say that we invented all of this mathematics by ourselves, and they suppress the fact that a huge amount of Arabic mathematics was in their libraries. In fact, this is what Raju has done. He has traced that Copernicus's library contained this book in Greek, which was a translation of the Arabic, and so to say that he invented it on himself doesn't make sense. So Umar Khayyam derived general methods for solving cubic equations and even some higher order equations. Now you see, this is one thing that one major problem that has been pursued by mankind: how to solve linear equation, how to solve quadratic equation, and this is how they did it, step by step. Al-Khwarizmi solved the quadratic equation completely, and then Umar Khayyam solved the cubic equation, and quartic equations were solved, and then ultimately, as far as I know, I haven't discovered the contrary, the Europeans have the credit for discovering that the quintic equation, the fifth order equation, cannot be solved by the normal methods which are used for 1 to 4. It can be solved, and we will show how to solve it. So today we can solve equations of any order almost. So learning this is something which is centuries of progress, and lots of people spend their lifetimes in trying to learn the answers which you are going to learn very easily and cheaply, and you will not value how much effort, how many people made for how long in order to learn the solutions. But it is important to note that Umar Khayyam in 1100 solved the cubic equation, but if you read the Wikipedia articles, it will not tell you this. It will tell you that it was Cardano and Tartaglia and some Italians. Now, even more important, this is his philosophy of mathematics is actually not known in Europe today, and it's something very valuable and important, and I will discuss this because actually it allows us to do things in a new and different way, and it solves problems that they still have and they haven't been able to solve, which is basically one of the things is, what is the nature of a model, and how do models relate to reality? This is something about which there is massive confusion in the West. So mathematics is like models. You see, you study the utility maximization model, but you never study how this model is related to real behavior. Now, it may be that in some situations this model can do a reasonable job. Sometimes it's okay to assume that people are selfishly, but sometimes it's not. So one has to understand, if you're using a model, you have to understand when this model can be used and when it cannot be used. But this is never taught to you because in the West they don't understand what model is. So this statement that I have quoted from Umar Khayyam is amazing, because actually I just discovered it doing research for this course. I didn't because I had been taught that the analytic geometry is an invention of the Europeans, and it's a very powerful and very important invention. It says that you can take a problem from geometry and convert it to a problem from algebra, and this actually was a very powerful methodology which led to a great deal of advance in mathematics. And I was told, and I believed, that it was Descartes and his followers who invented analytic geometry. But now you see this sentence from Umar Khayyam's book: whoever thinks algebra is a trick in obtaining unknowns has thought incorrectly. No attention should be paid to the fact that algebra and geometric are different in appearance. No, they are the same. Algebras are geometric facts. So this is the fundamental principle of analytic geometry, which Umar Khayyam is stating in 1100. And now they are saying that they invented it in 1700, 16. So this is ridiculous. And the second quote is also in Wikipedia. It may sound, not Wikipedia, some other internet source. It may sound strange, but Descartes never used the Cartesian coordinate in his treatise or ever in his life. He wrote about coordinates, but but he didn't even understand negative distances. This was a big problem in Europe. They couldn't understand negative numbers for a long time. So coordinates, etc., they all rely on negative numbers. So this claim that Descartes is the inventor of Cartesian coordinates is just ridiculous. But still, this is widely believed. So now, that's preliminary. Now we come to the question. So last time we discussed the linear equation and we showed that it has exactly one root. Now we come to the second order equation, and I am relying on your previous knowledge, otherwise we would go a little bit slower. This is a basic quadratic function, and you can see that it crosses the x-axis at 2 points, and so it has two real roots. And there is a case with one real root where you have tangency, and here is a case with no real roots where the function itself lies above the real line. So it never intersects, so it cannot have a real root. So this contradicts the fundamental theorem. We said that every second order equation, first order there was no problem. Every real first order equation has one real root. But second order we run into a problem. It doesn't seem like there are two roots. We have two roots and then one root and then zero root. So there is something wrong here. So basically it turns out that when you look at the geometry, it's different from the algebra. And then we will try to match the algebra and the geometry, because the geometry gives us the intuition and the algebra gives us the formal, the slow and fast system. So we will try to see how to look at the roots in the cases where there is no immediate root in sight. So one thing is that the two real roots is easy to understand that case. Now when you have one real root, that is the tangency solution, then actually that one real root is like two repeated roots. That's the intuition. I will try to make it more clear and precise. And when you have no real roots, it's like a pair of complex conjugate roots. So in all cases we have exactly two roots. When you have one root, it's just a repeated root. It's one root occurring twice. What does it mean? That's something that we will have to understand. But basically it becomes a question of algebra. In algebra, this thing becomes much clearer than in the geometry. So that's why you have to think simultaneously. Some things are clearer in the geometry picture, some things are clearer in the algebra, and you have to keep both of them in mind at the same time. This is the same thing with models and reality. When you have a model and you have reality, you have to keep both of the things. Sometimes the model tells you something about reality, sometimes reality tells you something about the model, and you get really confused if you think of both of them as the same thing. And this is the mistake that has been made continuously and constantly in the West, where they are confusing the model with the reality. As long as you keep the two things different, the fact that models are wrong doesn't cause problem. But if you think the model is the same as the reality, then you get into serious trouble. So as long as you believe that, okay, this is a model which can be used to describe human behavior in some cases, that's fine. But if you say that all human beings are selfish and they maximize confusion, and you think that this is true about real human beings, then you are in trouble. And this is the mistake that has continuously being made in the West, today even. So in the algebra, we have something very easy to understand. You have this equation which is ax squared plus bx plus c. This is the standard, most general quadratic equation where a must not be equal to 0. This is very important. Then this can be factorized as a times x minus r1 times x minus r2, where r1 and r2 are two roots. Now this is not obvious. I mean, can we factorize it? Can we not? But this is the fundamental theorem. It says that yes, we can always factorize. So now this is easy to understand in the algebra. Now we can understand the algebra better than the geometry. And so obviously if x is r1, this is going to be 0. If x is r2, this is going to be 0. And we can understand repeated roots. If R1 and R2 are the same, then this is two roots, and we can see why it is the same root, but it is twice, it's not once. And also, if R1 and R2 are complex numbers, then this is factorization will still be hold. And now the interesting thing is that the only way, you see, if R1 is complex and R2 is complex, it's A plus BI, then the product can be real only if they are conjugates. If R1 is A plus BI and R1 is A minus BI, then the product will be real. If it's anything else, then the product will have complex numbers, but if it's complex numbers, then it can't match the real equation. So that's why complex roots can only occur in conjugate pairs. You can only have two of them. You cannot have one complex root. So the quadratic equation either has two complex roots or it has two real roots. There are no cases in which it has one real root and one complex root. So we see that the repeated root, the tangency solution, must be a repeated root. This is, you see, now we are thinking purely intuitively. There is no math here. I mean, you're looking at the picture and you're seeing that there is one root. You can see that there's only one root because there's only one point at which the graph is touching the x-axis. Now I'm saying this one root is two roots. Now I can understand it algebraically. It's x minus r times x minus r, or x minus r squared. But how can I understand it in geometry? Geometry both looks the same in the sense that there is one root, which is one point at which the graph is intersecting. So if you look at one root, x minus r, think about the function, how this function plots. So this function has to cross 0 because for x less than r, this will be negative. For x bigger than r, this will be positive. So x minus r changes sign. So now if you have a tangency solution, then this does not change signs. So it cannot be x minus r. X minus r is forced to. So the only way to prevent the sign change is to square that. If you have x minus r squared, then the sign will remain the same below r and above r. So we can see that the tangency implies a double root because a single root is forced to change sign. So that's the way we see that the tangency is automatically reflecting a double root, a repeated root. So we see that geometry captures the algebra. Another interesting use of this factorization is that if you have ax plus b, you can factor out the x and write this as, oops, there's a slight mistake here. Factor it as x plus b over a, which is like x minus b over a. So now when you write it like this, a parenthesis x minus r, then you see that if x is equal to r, this must be equal to 0. So minus b over a is the root of this equation. And you see that this is different from the standard algebra solution. If you set ax plus b equals 0, put b on the other side and divide through, you get the same solution, but it's a different procedure. There you are solving an equation. Here we are using factorization method. So factorization method gives us another way to solve for the root. So now we have three methods to solve for roots. One is the algebra, one is the numerical method where you graph and you look at the place of intersection. The other is by algebra, standard algebra, ax plus b equals 0, solve the equation for x. The third method is by factorization. All three methods are different and all three methods are useful in solving higher order equations. Now one more important thing is that when you want to solve for roots, then we can use what is called monic polynomials. The monic polynomials are ones in which the first coefficient of the highest order term is equal to 1. That's the definition of monic polynomial. So an, you see, it doesn't matter, it just sets the scale for the equation. If you can factor out an, then you can divide all of the coefficients through by an and you get the same polynomial. Now a 0 of the right hand side polynomial is the same as the 0 of a left hand side polynomial. So if we can find the zeros of the monic polynomials, we can find zeros of all polynomials. So this is a general method where we take something complicated and we reduce it to something simpler. This is a standard mathematical technique where we take any complicated mathematical problem and we try to reduce it to the simplest form. It's a very general technique in trying to understand things. Try to understand the simplest possible form of the problem first, then make it complicated, and that makes it easier to understand things. So now what I will do is look at the simplest case of the real roots. Case let's look at the simplest quadratic equation. So the simplest case, first of all, we have monic polynomial, so the a function factor is 1, and then let's think about the situation where b is 0. That's the simplest case actually. So then this quadratic equation, just x squared plus c equals 0, and that has a very easy solution. This is something which is babies can understand. So x squared equals minus c, and x is equal to the square root of minus c, and there are two square roots. One is positive because when you square things the minus sign becomes lost. So we have, now if c is negative, then there are two real roots. If c is positive, then we get imaginary solutions. So we convert this algebra into the graphical case. If c is negative, then it's positive, then you have real roots. If c is positive, then the square root of a negative number is an imaginary number. And so currently we are not looking at that case, but yes, we will have to look at that case, because as I said, if you look at the fundamental theorem is true when you allow for complex numbers. It otherwise is false. If you just have real numbers, then fundamental theorem is not true, because you cannot factorize without using complex numbers. So here is one case where you have two real roots. The quadratic is going below the axis, and so it intersects. Now one very important thing here is that it goes down to minus 5. And now what are these intersection points? We have a quadratic which is exactly centered at 0. This is x squared plus c equals 0. C is 5 here. C is minus 5 here. So c is minus 5. So at x equals 0, the value is minus 5. So what are these roots? This is like not 2.1, but what is it symbolically? Not numerically. This is the positive root, and this is the negative. What are these roots? You know the algebra, so you can solve it. Yes, what? No, but what is R1 and what is R2? Not 2n minus 2. X squared is equal to? Yeah, but what is c? We have an equation graph here. C is? Square root of 5, exactly. This has to be the square root of 5, plus square root of 5 and minus square root of 5. So there is a relation. The place where it hits, this is the square root of that. This is the square root of square root of 5. Square root of 5 is around 2.2, slightly bigger than 2.2. So now you can see it. If we made the numerical analysis, we've made the graph in Excel, and I have it. I'll show it to you later. Then you can get 2.2 and the other decimal places just by looking at the graph and it will converge to square root of 5. So the numerical solution gives you something different from square root of 5. Square root of 5 gives you a symbolic solution. Numeric solution gives you the number answer, which you can see roughly from this graph. So this is visual, intuitive, but something you don't see immediately is that this is the square root. I'll explain why this is the square root later on, and that's also visual and intuitive. But now I want to look at something else. So here is this graph which is centered. Suppose I want to shift the center, and this is very important. This is a procedure which is very important in mathematics. Suppose I change from x to x plus t. I just shift the origin, the axis. Instead of putting 0 at where it is, I move it to t. So the intuition actually very important, and we will show this. All quadratics are just shifts. There's only one quadratic. There's not more than one. There's only one picture, and all other pictures come from just shifting the origins. So here is a picture of y equals x squared minus 5. That is the one in the center, which is exactly the equation that we have plotted earlier. This is the dark blue line. Now, suppose I shift from x to x plus 2. That becomes the light blue line. Because, you see, this is always confusing, still confuses me, that when you go from x to x plus 2, then it seems like it should move to the right, but actually it moves to the left. Why? Because you see, where is the new 0? If you have x equals minus 2, then this is 0, right? So the 0 is at x equals minus 2. So that's why it's shifted backwards. This is always confusing. You can get used to it after analyzing it a little bit. But there are two transformations. There is z equals x plus 2 and x equals z minus 2. And so one of them is the forward transformation going from x to x plus 2. That is the backward transformation going from the new to the previous. So in some cases one transformation is operational, in the other, so the intuition gets a little bit confused. But anyway, you see the when you shift from in fact the picture is labeled wrong. X is not shifted by plus 2, x is shifted by minus 2. So the dark blue line has 0 at minus 2, and this is the new quadratic. So that is the visual picture. Now what happens in the algebra when we do the translation? You see, you have z is equal to x plus t. T is the translation parameter, which is 2 here. So x is equal to z minus t. So now if we take the 0 equals x squared plus c, then it becomes replace x by its equivalent z minus t, and you get the equation z minus t squared plus c equals 0. This is the same equation as before, but x has been translated by t. Now if you just expand it out, then you see that it becomes z squared minus 2z z squared minus 2z plus t squared plus c. So now you see that when you translate x, both the b and the c is changed. Both the constant changes and the coefficient of z changes. So the constant c changed to t squared plus c, and the b parameter changes to minus 2t. So basically the concept is that, like we went from the simple to the complex, we can go in the backward direction. We can start with a complicated equation and make it simpler. So if I start with some equation like z squared plus bz plus d equals 0, then if I set b equal to minus 2t, just matching the previous equation, and d equal to t squared plus c, then the equation will translate to simply x squared plus c equals 0. So I can take z squared plus bz plus d and find out the t and c which will translate this to an equation in which we have a simple equation in which we know how to solve. So this concept is known as translation to canonical form. Basically, all quadratic equations can be reduced to the simplest case, which we have already studied and solved, by two things. One is the translation, that is adding or subtracting some constant to the x, and the other is a change of scale. Change of scale I don't need because I have a monic polynomial. If I had general, then I would need to change scale. Instead of making the unit of measurement something, I will have to multiply it by a, that's all, and that will change the unit of measurement for x, and that will give me the general quadratic ax squared plus bx plus c. If a is set to 1, then I don't need to change scale, only the translation is enough. So this is the equation that you need if you have x equals alpha z plus beta. Beta is the translation parameter, alpha is the change of scale parameter. Then if you take the simple equation x squared plus lambda, that is the simplest quadratic, you replace x by alpha z plus beta, then you get alpha squared z squared plus 2 alpha beta z plus beta squared plus gamma. So we can take the simplest equation and make it into the general quadratic by a change of scale and a translation. So here the a is equal to alpha squared, b is equal to 2 alpha beta, and c is equal to beta squared plus gamma. So I can translate any general quadratic into the simplest quadratic. So the equation az squared plus bz plus c equals 0 is the same as the equation x squared plus gamma equals 0. And I know how to solve the second equation. I have made this is a error here. This should be beta squared plus c here, and this should be gamma equals beta squared plus c. Then this will be correct. Alright, now I want to show something which is done much easier in Mathematica, which is how these graphs change when you change the numbers. So here is a graph of a quadratic function where I have this is the coefficient of the quadratic term 1. So this is a monic polynomial. This is actually x squared plus 4x plus 14. The 1, 4 and 14 at the top, these are the coefficients of the quadratic. I've just made it. I don't know what's this. Oh, I see. This thing is nothing. This is the y. That's C3, which is over here. That's 14. So C3 plus D4, that's here. That's 4, which is in D3, times x, which is over here. And this is the quadratic. E3, which is the coefficient above, multiplied by A4 squared. So this is nothing because we take the constant from the top, and then this is a linear term, this constant times x, and this is the quadratic term, this constant times x squared, and this is the cubic term which we will use later. Currently I have set the cubic coefficient to 0, so it's not coming in to the equation. So now here we have the quadratic equation 14 plus 4x plus 1 times x squared. and then this is going from minus 5.9, which is x low, up to x high, which is plus 3.9, and that's the picture. And so according to our theory, this 4x and this 14, these are terms which can be reduced. So one thing that we want to do to this equation is we want to centralize it. So by how much do we need to shift this to make it centered on the x-axis? This is the question. Yes. Who got it? -2. Okay. One chocolate for you. So now the other people see where the -2 is coming from? Yes? Yeah, the minimum of the is at -2. So if we shift it to -2, it will be centered, and that's where that will make the. So we need to translate this by -2, which means that. Okay. Oops, that's not where I want to go. Oh, so I can change these things. Like what happens if I make this 2? What will happen to this function now if I make this 2? What is you see the scale of x will increase. Yani, will the graph become sharper or will it become flatter? It will become sharper because it will speed up the convergence to infinity, because x is replaced by 2x. So at 2 it will be 4. At 10 it will be 20. At 20 squared 4. At 10 it would be the 10 squared term will be 100, but 20 squared will be 400. So it will go up faster. What happens when we change this? This is hard to say, and we will understand what happens. Okay, so one of the things that happened is that the center of symmetry changed to what when I made the coefficient 10? Whoops. Oh yeah, it's still at minus 2.5. Huh? It's like 2.5. Yeah. Right. It's actually b over. It's because of the a 2a. Yeah. And what happens if I change this 14 to 25? What will happen to the function? Will it go up, down, sideways? Yes. Yeah, it moves up. Yeah. In the Mathematica, you have sliders and you can move it continuously, and you get a better, clearer picture, which Ramzan will show you next time, hopefully. Ramzan? Yes. So I was planning to do the Mathematica, but I decided I will let the expert do it. So I will just do the Excels. So by changing this, you can get a picture. You can get an understanding of what the quadratic is by changing the coefficients seeing. And this is something which we can do today. 20 years ago, when I was in school, we could not do it because making a graph of a function was a very difficult job, and then changing it was again a very difficult job. So then achieving this understanding required much more brilliance. You had to be able to see these things in your mind, and this is what mathematicians had. This is the skill that mathematicians. But now the Excel can do your thinking for you, so you can be a much better mathematician much more quickly. And in fact, this is one of the goals, that instead of this course, that instead of teaching you mathematics, I want to teach you how to use mathematics, how to use, this Mathematica program. It has the genius of hundreds of mathematicians built into it. All you need to do is learn how to access that, and then you can solve problems which nobody in Pakistan can solve, mathematical problems of such complexity. Because Not only are they not taught how to solve them, but they are not taught how to use the tools that are currently exist to allow them to solve. So now we go to the complex root case. So we just summarize that we can take any quadratic and reduce it to canonical form, simplest form. If we can solve one quadratic, we can solve all quadratics. Simplest form, possible form is called canonical form. By the way, canon is the Arabic word qanun, and canonical law, which is what the Europeans borrowed from Islamic sources, is actually a translation of a book called Al-Qanun, which was translated into European language and used for centuries as a textbook. So here is the equation: x squared plus 4x plus 14. Where does this have a minimum? Minus 2. So we need to translate it by 2 to center it. And that's basically it. This is a monic polynomial, so it means that it doesn't need change of scale. All you need to do is one translation and you can solve it visually. This is very important, that but after making one translation, you can just solve it by looking at it. You don't have to do equations, because it's basically the square root of the constant, right? So we need to here I can see where the center of symmetry is, but I would like to be able to calculate it also. So we know how to do that. The first order conditions: if you take the derivative of ax squared plus bx plus c, it's just 2ax plus b equals 0 for the first order condition. So x equals minus b over 2a. If you have a monic polynomial, if a is 1, then you have minus b over 2. So in the previous equation, I have 4 is the b, so minus 4 over 2 is minus 2. That's the center of symmetry. If I have a there, that's the example we saw earlier, 10 and 2, so then it will be 10 minus 10 divided by 2 times 2, minus 10 over 4, that's 2.5, and that's where it was, the minimum. So the translation parameter needs to be b over 2a in order to shift the x to 0. So here's the same picture again, but I've now drawn the translation. So the translation function has, instead of, basically you have x squared plus 4x plus 14, this can be written as x plus 2 squared plus 10. So the function that the centered function is y equals x squared plus 10, and the translated function is y equals x plus 2 squared plus 10. Yeah. So, but the thing is that the constant doesn't remain the same, because when you translate, both the constant and the slope change. So now, if I have an equation like y equals x squared plus 10, I can solve that easily, because x squared plus 10 equals 0 means x squared equals minus 10. So x is the square root of minus 10. So it's a pure imaginary number. Okay, so the canonical form for complex case is also z squared plus c equals 0, and z equals plus or minus square root of minus c. If c is positive, then this will be imaginary number, and it will be just a pure imaginary, no real part. So this is the interesting thing. When you have a complex solution, the real part is the translation parameter, and the imaginary part, so you are doing two shifts actually. One shift is in the y-axis, up and down, and the other shift is in the x-axis. So the x-axis shift is the real parameter, and the y-axis shift is the imaginary part. So now we have an understanding of the quadratic equation in geometric terms. So there is a two-step algorithm which we can use to solve the quadratic. One is that first you translate the x to symmetrize the graph, and then you solve the symmetric quadratic. Center of symmetry we already did. So, graphically, visually, symmetry means that the function at z is the same as the function at minus z. That is, the picture is symmetric. The values on the negative axis are reflection of values on the positive axis. In algebraic terms, it means that the b is 0. Bx cannot be there because bx is not a symmetric function. As x changes from x, it's a straight line, so on the negative side it's different from what it is on the positive side. So automatically, if you translate the graph to symmetry, then you know without doing the calculations that the b must be 0. So this is the thing about how the needing to think in both graphical terms in algebra. You should know what algebra means in the graph, and you should know what the graph means in the algebra. That way you will have a deeper understanding. So if I calculate the center of symmetry, which is t, and then I substitute z minus t for x, then without doing the algebra, I know that the term in z will vanish, because if the graph is symmetric, there cannot be a term in z. Okay, so now I will do the calculations, the algebra, and then we will do the geometry. So here, I start with ax squared plus bx plus c, and then I substitute z minus t, where t can be anything so far for the moment. I'm just saying what happens to a quadratic equation when I do a translation. So then I just expand, so the a term does not change, az squared remains az squared. The b term changes, it becomes b minus 2 times at. That's coming from the quadratic. And the c term again changes, it becomes c minus bt, which is coming from the linear term, and then plus at squared, which is coming from the quadratic term. So the constant, if I make a translation, then the b terms changes to b minus 2at, where t is the translation, and the constant terms changes to c minus bt plus at squared. Okay, is that clear and simple? So now, the question is, how should I make the translation to make the center term disappear? So obviously, I should set t equals to b over 2a. Now this is purely from the algebra, I haven't done any minimization, but b over 2a is exactly the point at which the minimization would occur, minus b over 2a actually, because that's where I need to translate to in order to get rid of the in order to make the graph symmetric. So I have b minus 2at equals 0. If I set c prime, the new c, equal to c minus bt, then c minus bt is equal to c minus basically plus 80 squared भी आएगा इसमें. Okay. Yeah, there's a missing term here, but I have covered it up in the second equation. bt minus bt is minus b times b over 2a, which is b squared over 2a, and then you have 2 times 80 squared plus, and so t squared is b squared over 4a yeah, right. So that's it. It's t squared is b squared over 4a squared multiplied by a, it becomes b squared over 4a. So the total transformation c minus bt, bt minus bt is minus b squared over 2a. at squared is b squared over 4a, and so when I combine minus b squared over 2a plus b squared over 4, it just becomes minus b squared over 4a. So the translated equation is a times z squared plus c prime equals 0. Because the middle term has disappeared, and now that just says z squared equals c prime divided by a, and that is from the calculation. Z squared is minus c prime, so I take b squared over 4a and subtract c and then divide by a, and I get b squared over 4a squared minus c over a, which becomes b squared minus 4ac over 4a squared, and it leads to z equals plus or minus square root of b squared minus 4ac over 2a. This is something which you already know from your quadratic equation, but this is a completely different derivation. And there is a missing minus b over 2a, and that missing part is the translation parameter, b over 2a. So there are two parts to the solution. One is that you translate to make it the center of symmetry, and the other is that you take the square root of wherever the gap from the 0 is. Okay, so that's so x equals z minus t, which is minus b over 2 plus or minus, and this is the standard solution to the quadratic. Okay, so I think we stop this here, and now I will go to the second part of the lecture, which will be, so this was the algebraic solution, and now we will do the graphical solution, which will give us more insight. So there's slow system and fast system. So I've done the slow system solution, which is the algebra, which is the one you know, and now I will teach you the one that you don't know, which is how to solve the quadratic equation by graphical methods only. So, أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم اللهم انفعني بما علمتني وعلمني ما ينفعني وارزقني علما تنفعني به. Oh, I should switch to the slideshow mode. Okay, so we are going to look at one equation. This is a bad choice, but I didn't because it's not a monic, and it will make things a little bit more complicated than necessary. But okay, you can follow it. What happened? Oh, I see, I'm going in the wrong direction. Okay, so this is the graph which I made of this equation in Excel. So what is the center of symmetry? Yeah, it's 5, and the equation is minus b over 2a, so it's minus 5 divided by 1/2 minus 5 divided by 1/2, so that's going to be plus 10. Oops, 2a क्या हो गया? b over 2a था. Oh, 2a is 1. 2a is 1, yes. So 2a is 1, so it's minus 5, which is plus 5, which is the center of symmetry. So that's the center of symmetry, x equals 5. Quadratic is minimized at x equals 5. And now the other part is where is the base? Y is equal to minus 2.5. That's the point. How do we determine this? Well, there are many ways, but just substitute minus 5 into the equation. So you get 1/2 times 5 squared, that's 12.5, minus 25 plus 10. So it's 22.5 minus 25, and that's minus 2.5. So that's the minimum value. So now the point here is that if you look at that x and you look at that y axis, then you have a simple quadratic. It's 1/2 x squared now. That's all. So this is the point, that by translating x and translating y, you get to the canonical form, the simplest possible quadratic. So all quadratics are the same. Minimum value is minus 2.5. So yes, this is the thing. If I put the translation of x at xm equals 5 and put the translation of y at ym equals minus 2.5, then the quadratic becomes y minus ym equals 1/2 x minus xm squared. So the translation of y equals 1/2 times the translation of x squared. So it's just y equals x squared times a constant. It's the same. So we start with any equation and we can reduce it to this form. So the center of symmetry is 5. The minimum value is minus 2.5. And so now I'm trying to find the roots visually. So the two roots are it's going to be basically 5 plus or minus. You see, if you look at the picture, so the points at which you have crossing is basically the center 5 minus some r and plus some r. So here we have a situation where I have two real roots. This is the easier to understand situation. So I'm starting with this, then we will do the complex situation. So here I have two real roots and I'm analyzing the two real roots. So the main part of the two real roots is the center of the quadratic. Now this is the minus b over 2a term. But now I can see it directly without having to do any algebra. If I look at the graph, I can see that it will be the minus b over 2 will be x equals 5. Without knowing what the equation is, I just look at the picture, I can see that the solution will have 5 minus something and 5 plus something. So I can find that term without doing any algebra. Now, what is that something? That is actually the square root of 2.5. But why is it the square root of 2.5? For that, and of course, the symmetry is also obvious from the picture, that the both roots are on equidistant. One is plus the same thing and the other is minus the same thing. So actually, if what I'm going to do to give you the picture is to flip the graph. I'm going to make the x equal to the y and y equal to x. So flipping the graph, this is the quadratic, so this is y equals x squared, so this will be x equals square root of y. Actually, this is the function. It's equal to y equals 1/2 x squared is the equation. So 2y equals x squared, so x equals square root of 2y. This is the equation that we are now going to plot. So this is the original equation, which is y prime equals 1/2 x prime squared. I'm using the prime to talk about the translation. And this can be 2 times. So I multiply by 2 and I put in the translation parameter. So y is being translated by 2.5 and x is being translated by 5. So the equation is 2 times y plus 2.5 equals x minus 5 squared. And these are the translations. And now, if I just flip the graph, you will see that the graph is x prime equals square root of 2y squared. There are two branches. The top branch is the plus square root, and the bottom branch is the minus square root. And you can see that at 2.5 over here, where we're reaching the 0, this will be, this is not 2.5. This is 2.5 times 2, because we are multiplying by 2. So this is 5. So at the top, the intersection will occur at square root of 5, and at the bottom, the value of the function will be minus square root of 5. So you can see that if you look at what is the distance from this 0 to the top, it's plus square root of 5, and what's the distance to the bottom? It's minus square root of 5. So we have the solution. It's going to be x is 5 plus or minus the square root of 5. So this is the graphical solution of the quadratic when you have real roots. Now we go to the situation where you have complex roots. So complex roots is quite is similar to the real roots, but is a little bit different. So you have x squared plus c equals 0. Now there are no intersections. So how do we plot it? Well, basically you have x squared is minus c. So x equals I, the imaginary number, times the square root of c. And this is the thing, the algebraically, x squared plus c equals x minus I times the square root of c times x plus the square root of I times the square root of c. And that's equal to x squared minus, this is very important formula for the quadratic case. X minus a times x plus a equals x squared minus a squared. So in that case, the a squared will have the imaginary number, and the I squared will become minus 1, and so the I will drop out. And that's the only case in which I will drop out. If you have different values, I times something and I times something else, then there will always be an I term. And so the equation cannot be a real quadratic equation. So if I look at x squared plus c, and I try to find complex solutions, I put in a plus ib, so that becomes c squared plus a squared minus b squared, and then there is a I times 2ab equals 0. Now the I is multiplying 2ab, and that has to be 0, and the only way that it can be 0 is if a is 0, because we can't allow b to be 0, because otherwise we won't get a solution. So a has to be 0, and then c minus b squared has to be 0. So b has to be equal to plus or minus the square root of c. Notice that here the c is positive. So now the square root of c is, but this is almost the same solution as in the negative case where we had square root of minus c. So here is the way to picture the solution. Here I have x squared plus 5. X squared minus 5 equals 0. No, x squared plus 5 equals 0. So x squared plus 5 cannot equal 0 because x squared has to be positive. So the only solution is if x is imaginary. So now if I reflect this, you see, if I put in imaginary solutions, if I put x equals ib, then this equation becomes minus b squared plus c equals 0. Right? X equals ib squared is minus b squared. So now what happens if I plot this in b? Well, this is the quadratic equation minus b squared plus c, minus x squared plus c. So if I take this graph and I just reflect it on the minimum, then I get the roots, the imaginary roots. This is the imaginary root over here, and this is the imaginary root over there. So basically by reflecting the graph, I get the two imaginary roots on the axis. So that's the picture. Now I can make it more clear. Okay, so I'm now going to do one case by graphical method just to put everything together. So I have this equation x squared plus 4x plus 9, and this equation has no real roots, or maybe it does, I don't remember. Let's look at the graph. So yes, this one has no real roots. It's going above the x-axis. And the minimum value occurs at what? At minus 2, minus b over 2. B is 4 and the a is 0, so a is 1, so it's just that. So minus 2 is the minimum value. So I will need to translate x by 2. So I need to move x plus 2. So xm equals minus 2. That's the center of symmetry of the graph. This is the bottom. This is the place where the y-axis needs to be. Ym equals plus 5. That's the value. And where do I get that? Well, I put minus 2 into the equation. So minus 2 squared is 4. Minus 8. So it's 4 minus 8 plus 9. And so that will be 4 plus 1. That's 5. So xm is equal to minus 2. Ym equals 5. And after I make these two translations, this will become a standard quadratic. So the real part of the solution is minus 2, and the imaginary part is square root of minus 5, and that's 2.236. That's the just the decimal expansion I. So the solutions are minus 2 plus or minus 2, 2.36 I. And this we can obtain just from the graph without doing any algebra. Because ym is above the axis, so the imaginary part will be square root of minus 5. It will be the plus or minus I times the square root of 5. And the real part will be minus 2. So it will be minus 2 plus or minus I square root of minus 5 directly from the graph. Now we go back to the algebra, and basically that is x squared plus 4x plus 9. I want to factorize it into this part, x minus r1 times x minus r2. There is no a out there because we have a monic polynomial. So I know that in this particular case I have two complex conjugate roots. So the function is x minus 2 minus I root 5 and minus 2 plus I root 5. So these are R1 and R2. This is a pair of complex conjugate roots. So I rearrange this. It becomes x plus 2 plus I square root of 5 and x plus 2 minus I root 5. So now this is a plus b times a minus b. That's going to be a squared minus b squared. That's the formula that we were using. V plus w times v minus w is v squared minus w squared. Very important and useful formula for this case. So I get that the quadratic is x plus 2 squared plus 5. Now, once you have this factorization, you can solve it by just looking at it. Because I know that x plus 2 squared needs to equal minus 5, right, to make this 0. So this has to be, x plus 2 has to equal I times the square root of 5, right? So x plus 2 equals I root 5, so x equals minus 2 plus or minus I root 5. So just by looking at this equation I can solve it. So even in the algebra, you see, once you have it in the right form, you can just pick out the solution without having to do any mathematics. See, this is what mathematics is about. It's not about writing out equations and manipulating. It's about understanding what is going on. So we can read off the solutions from this, and also we note that we can write this function as y minus yt equals x minus xt squared, where yt is 5 and xt is minus 2. What this shows is that all quadratics are the same. I mean, you can start with an arbitrary quadratic and reduce it. If you translate the y and translate the x, you are getting y equals x squared. And this is what the graphical picture showed us, that if I move the x-axis to the center of symmetry of x and move the y-axis to the bottom of the graph, I get a standard quadratic. So to wrap up, now I go back to what we have done. First of all, the function f of x equals 0. I'm going 0, 1, 2. So f of x equals 0. The 0 function is not a polynomial because the term which multiplies the leading is 0, and we don't allow that for polynomials. Now if we have p0 of x equals a0, where a0 is not 0, this is a 0 degree polynomial because a0 is multiplying x to the 0, and it has 0 zeros. It has no zeros because a0 cannot be 0. Then we go to first degree polynomial. First degree polynomial is a1x plus a0. It is first degree only if a1 is not 0. And if a1 is not 0, then this is either a line with positive slope or a line with negative slope. In either case, it can only cross the x-axis at exactly one point, and that is the unique 0 of the first degree polynomial. Then we go to P2, and this is the case which we have done in complete detail this time. So I have a2x squared plus a1x squared plus a0, and this can be always factorized as a2 times x minus r1 times x minus r2. Now there can be two real roots. When you have two real roots, they can be anything. Or you can have one repeated real root. That's the tangency solution. So it's x minus r times x minus r. When you have a tangency solution, it has to be a tangency. It cannot cross. And when you have a cross, it cannot be a double root. So it's very clear. I mean, the graph and the algebra are matching to each other. Now the third case, the most complicated case, is the pair of complex conjugate roots. So you have x minus z, which is a plus bi, and then x minus the conjugate of z, a minus bi. That's the only possible case where you have complex root. In that case, basically the a term represents the translation to the center of the graph, and the bi terms is the square root of the constant. So complex roots always occur in conjugate pairs. I've already explained why this is so, and the geometry of this is also clear, that once you put the center of symmetry, the two roots occur at equal distances from the center of symmetry. Okay, now we go to the case of the odd roots. So we have covered the quadratic. Now we go to the cubic, which was solved by Umar Khayyam, but is attributed to Cardano and Tartaglia in Italy, even though they didn't actually get the correct solutions. So now we go back to something which is very important. This is a generalization of the principle. Okay, let's start with the slideshow. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم قل رب زدني علما. So now what I would like, so we want to start by solving the cubic. So now I would like to argue first that every odd degree polynomial has one real root, guaranteed. So first order polynomial had one real root. Second order polynomial doesn't necessarily have one real root. It can have two or it can have zero real roots. But the third degree has to have real roots, and basically it's because complex roots always occur in conjugate pairs. That's the only way you can get the multiplication to work out so that the product is real even though you have complex roots. So since they occur in pairs, there can only be 2 or 4, they cannot be 3. So one of the roots has to be real. But now that's the algebraic, But now there is also a geometric understanding, and it comes from the intermediate value theorem. Basically, this is how mathematics work. We work a special case and then we have a general case. So we have looked at one special case, that all linear functions have roots. That's because they go from minus infinity to plus infinity or vice versa. Now I want to show that odd polynomials have the same property. They always have to go from minus infinity to plus infinity. And so if so, then they have to have one real root at least. So in order to understand that, first we have to have a little bit of asymptotic theory. Asymptotic theory is about evaluating some function approximately for large values of x. That is what asymptotics means. So if I have a polynomial ax to the 6th times b, so what I want to say is that if you want to approximate that polynomial for large x, then you only look at the leading term. All others are going to be unimportant. And intuitively that's very simple. Suppose I have x equals 10, which is not a very large value, and I have then x to the 6th will be 1 million, and x to the 5th will be 100,000. So 100,000 is very small compared to 1 million, and of course all other terms are very small. Of course you can say that the constant term can bring it up. Yes, if I have 10 times x to the 5th, that's the same as x to the 6th. But this constant term cannot keep up for a long time. If I make 10 equal to, if x equal to 1000, then the x to the 6th will be 1 followed by 3 times 6, 18 zeros. And the second term, x to the 5th, will have only 15 zeros. So multiplying by 10 will add 1 zero, will still be 1/100th of the 6th order term. So basically this is the intuition that the large order term governs the behavior of the polynomial. So, but we can, this intuition can be captured into a formal argument, and that is the here given that okay, I factor out an x to the n, so then the first term will be 1 because I factored this out. The second term will be an minus 1 times x to the minus 1 divided by an x to the n. So it will be x to the n minus 1 will be cancelled by the x to the n minus 1 in the denominator, and there will be 1x remaining in the denominator. So other term will have x squared up to the x to the n. So now what happens to this when x goes to infinity? When x becomes large, it's clear that all of these other terms will disappear, because x is going to infinity, so 1 over x squared, all of these terms are going to 0. So it means that this term in the brackets will be just approximately equal to 1 for large x, and so basically the polynomial will be an x to the n for large values of x. This is the asymptotic theory. So now, so the polynomial behaves like an x to the n for large values of x. So if x is odd, then if x is near minus infinity, x to the n will also be near minus infinity, because the minus sign will be preserved by the odd power. And if x is plus infinity, then again, if x is near plus infinity, it will be plus infinity, because again the odd power will be preserving the sign. So it means that as x goes from minus infinity to plus infinity, x to the n for odd powers goes from minus infinity to infinity, so it must cross. So they must have a real root. Now if n is even, this argument doesn't work, right? Because if you have x squared, it goes from plus infinity to plus infinity in both sides, so it need not touch 0, so there's no. And for any even power, we don't have the, but for odd powers, every odd polynomial has to have a real root. This is a very powerful theorem, and just almost immediately from basic arguments. So this is what the beauty of math is, that you can understand something quite complicated and deep and difficult by very simple arguments. So the one thing that I didn't take into account was what happens if a n is negative. Same argument, but it just flips. The function goes from plus infinity to minus infinity, but still it has to cross 0. So here is a particular cubic polynomial, 1/2 x cubed minus x squared minus 5x. And this polynomial has 3 roots. The first root is occurring over here at minus 2.5 or so. The second root is at what? 0. Why? You can see from the algebra. There is no constant, exactly. So when you put x equals 0, it will be 0. And then the third root is occurring at 4 point something. Now, this is something which we can do today, which was not possible or not easily possible earlier, which is we can just magnify this graph in Excel and just compute numerically all the 3 roots. And this is something you should know how to do. That is, I find that, our students are cripples. I asked one of my one of my PhD students to maximize a function. Function was given. So he said, I can't do it because actually the function was not a good function. It didn't have easy differentials. So if you can't differentiate, you can't set first order condition equal to 0, then you can't solve. That is the only method you've been taught. I said, look, plot the function. Look at it. If you have a function that is given, you just plot it and you find where the maximum is by your eye. Your eyes are very good mathematicians. This is, in fact, you have a built-in mathematician inside your heart. If you just let go of the wrong things that you have been taught, then you will be able to do mathematics without any difficulty. So now what I am doing here is adding a constant. So what will happen if I add 20 to this? No, origin will not change. What will happen to the graph? It will be lifted up. So if we lift it up, currently the bottom is at minus 10 nearly, right? So this bottom will shift up so that now the 2 curves will be above the 0. So there will be, so here it is. Basically the same graph but just lifted up by 20, and now it has only one real root. And so what are the other 2 roots? There are 2 complex roots. Now, how can we find these complex roots? I have just told you how to do the quadratic case. I haven't told you how to do the cubic case. Oh, this is already I have done. Okay, so the odd polynomial has one real root, but if you look at the even polynomial, it has no roots, but we have done that already. So now, the thing that we need to do here, what I want to do is to use this. Now Mathematica has a very interesting property that it teaches you how to use it. Okay, so we start by a new document, and now what I want to do, this is what it looks like. What I am going to do is to see what I want to show you is how to solve cubic equations. And actually, okay, so when you write equals, this is what I wrote. It comes out with the orange equals. When this orange equals means that I don't know how to do Mathematica commands, so I'm just going to tell you in English and you try to interpret what it means. So I can say, for example, a graph 3x squared. Sorry, I want to go to a cubic. Okay, so let's use a monic cubic. X cubed plus 5x squared plus x plus 20. Oops. Oh, there is no internet connection somehow. How to interpret this? So now I have to give it the proper command in order to get it to work. So I can say, I think it's GRA, yeah, graph. Okay. So if I first of all commands start with capital letters, and once I have this, I can use this. You see, it gave me the options, and so now I have the option, and now I can ask it to show me what the graph looks like. So this is what the command looks like. Now यहाँ पे I just need one thing, right? If I remember correctly. Yeah. What happens here? Okay, so I'll put in x squared just to understand how this works. ये दूसरा number 2 3 argument क्या है यार? I don't है रमजान
प्लॉट करना चाह रहे हैं
हाँ प्लॉट
सर तो उसके लिए प्लॉट की कमांड
oh अच्छा graph is not the right command right
curly brackets and then we have to give the
right हाँ अब मुझे याद है कि प्लॉट की कमांड है ग्राफ की नहीं है okay so just delete this I want to plot the okay, so it's plot 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 yes, the function and then the x range. Okay, so this is very easy. Now I want to plot x cubed plus 10x plus x squared 10x. Oh, now it wants I think यहाँ पे star डालना होगा मुझे to denote the multiplication. 10 times x, oh it shouldn't be capital, x squared plus x plus 20, and now I have to give it a range. X min should be, let's say, minus 10 minus 20 कर दिया मैंने, and this should be plus 20, and shift enter is the command to execute. Okay, so here is the graph. Now because of the scale, it's not clear whether or not we have roots because the thing is too close. So what I need to do, if I want to examine it, is के minus 10 से शुरू करते हैं, because I think that's roughly where the graph is coming close to 0. इसको यहाँ पे minus 10 and go up to about plus 5. Okay, so now we see that this equation has only one real root. Now I can ask for the roots. इसने मुझे कोई एरर मैसेज दे दिया है. Oh, अच्छा, I'm not in the right place. Okay, now I'm in the right place. Now I want to do roots. Oops, ये क्या हो रहा है यहाँ पे मुझे? I don't know how to use Mathematica, you see, so नहीं, I want to put in roots, but यहाँ पे ये मुझे करने नहीं दे रहा है. I am. See, here's where I want to write in a new line, but it goes back to the graph.
No sir, वो वैसे critical हो जाता है, वो जो वाला command होती है.
I know that. It's not giving me the options for roots. It should be showing me how to use this command. या तो मैं इस फाइल को क्लोज कर दूं.
सर आप command देंगे तो execute करेगा ये.
Don't save. New notebook. Okay, now let me try. Roots. अच्छा, O तक मैं नहीं पहुंचा था, इसलिए it didn't give me the root of. Now x cubed plus क्या था इक्वेशन याद है? 10. हाँ? 10x squared. 10x squared plus x plus 20. Oh, I have used the wrong bracket. It uses square brackets for. ये क्या हो गया? Oh, I think I need to. I need to use the. Okay, let's look at root. Fk. So what is the k? अच्छा, यहाँ पे I think I can use percent. Percent होता है ना previous equation. Oh, मगर this will be a problem क्योंकि वो root डाल देगा इसमें. I need not the root here. हाँ? हाँ, copy paste कर लें. तुमको भी आती है ये Mathematica. Control C. Okay, and now यहाँ पे k नहीं x है तो अच्छा. Is that what it is? चलो. Shift enter. X is not a valid root number. I think I want 3 here. Yeah, 1. Okay, so it is telling me that the root is 20 plus number 1 plus 10 times number 1 squared. हाँ. Numeric value is minus 10.0971, and I think probably the other two roots are imaginary. Acha. So it gave me one of the roots.
सर इसको वैसे कंसोल इक्वेशन करके तो आगे मैं x equal to 0 पुट करूँगा.
तुम्हें मैथमेटिका आती है?
पढ़ा क्लास में.
अच्छा. तो अच्छा. Okay, so that's fine. Now what I want to do is to do a division, a polynomial. So do you know how to divide polynomials? Okay, let me just define. P of x. Definition कैसे करते हैं? Equals. Colon equals. Colon equals. So I'm going to define this polynomial x cubed plus 10 star x squared plus x plus 10. Oops, p is not allowed as a definition क्योंकि ये कोई इसका internal command है. So I need to do p 3. ये हो गया? What? Tag times p3 x is protected? ये क्यों हो? चलो f कर दूँ. F is also protected. I don't know. Acha. What I wanted to do, which I cannot do here, I will show you, is one very important last piece of information that I wanted to convey in this. I will just use a Word document to do it. Alright, what I want to show is that, okay, if you have a cubic polynomial, so it's x cubed plus 7x squared plus 5x plus 9. So this is a cubic polynomial. What I want to do is to divide. So the fundamental theorem says that this is equal to x minus r1 times x minus r2 times x minus r3. This is what the fundamental theorem tells me. So basically what I can do is, once I find one root, I can divide this equation by x minus r1, and this will give me a quadratic equation. And actually, you see, the theorem that is provable and proven is that you can take any cubic polynomial and divide it by x minus r, any r, and you will get a quadratic equation, yani x minus r times a quadratic plus a remainder. And the remainder has to be of lesser degree than the linear term. So since x minus r is a first order polynomial, so the remainder can only be a constant. So in general, if I divide by x minus r my cubic polynomial, I will get some constant remainder. But if r is a root, then there will be no remainder because it will factorize. And so, you see, once you have this understanding, then you can calculate the quadratic, what it must be, because you have x x cubed plus a2 x squared plus a1 x plus a0, and now you want to divide this by x minus r, and in general you can calculate what it must be, because basically you set x minus r times b2 x squared plus b1 x plus b0 so x minus r times this quadratic b2x squared plus b1x plus b0 plus some constant should equal the first polynomial. Now you can just multiply through. X times x squared is b2 times x cubed, so b2 has to equal 1. That's the only cubic term. Then for the quadratic term, you have minus r b2 x squared, that's one of the terms, and the other term is b1x times x. So minus r b2 plus b1, it has to equal a2. And similarly for all of the terms, you have to match the terms, and then you can solve for b1, b2 and b0 and c, and if r is a root of the equation, then c will be 0, and you will be able to calculate b2, b1 and b0. So you get you can factorize your cubic as x minus r times a quadratic, and then you solve for the quadratic roots. So that is that is part of the solution. I mean, so you know already how to solve a quadratic. So now I have taught you how to get all the roots of the cubic equation. And now if I didn't have, if I had access to the internet, I could show you that there was this big debate between Cardano and Tartaglia and somebody else, and they had this competition where they gave each other cubic equations, and both of them had secret formulas for solving cubics, and so they had to produce solutions. So Tartaglia won. He was able to solve all the cubic equations that were given to him by the other party, but the other party lost because they didn't have. So now you can solve all the cubic equations and you can win this competition that took place a few centuries ago. So I have given you actually a problem set here, which is on the website. And so this is your problem set, which is due for next time. It's very easy. It's called the birthday cubic problem. So you create a cubic equation which is based on your birthday, set the month, set the day, set the year. If you are shy about revealing your age, then you can change it a little bit, fudge it. I don't care that it's exactly the right birthday. So then I want you to just write down this. This is just a way to individualize the problem, so everyone has a different cubic. So and it has some personal relation to them. Then just draw a graph to find out how many real roots it has. Then you draw a graph focused on a small neighborhood to find out what that real root is, to how many decimal places, and you can explain, you can get it accurate to one decimal place easily, but just by making sure that you evaluate it every one decimal place. And you can get it to two decimal places if you like, but I don't ask you to do that. And then I've asked you to change the graph according to y. We've already shown you how to do that. So basically it will move up and down. So now I have, in order to put everybody, some people will have graphs with 3 real roots and some people will have a graph with 1 real root. So in order to put everybody in the same boat, I have given 2 sets of instructions according to whether you have 3 real roots or 1 real root. So in any case, by shifting the graphs up and down, you will be able to get 3 real roots or 1 real root. So for those who have 3 real roots, I have asked them to shift their graph up until they have only 1 real root, and for those who have 3, I've asked them to do it the other way, so as to get 3. So that now both of people will have 2 functions, and one of them is the polynomial v, which has 3 real roots, and one of them is the polynomial which is shifted, which has only 1 real root. And now I want you to compute the roots for both of those polynomials. Basically, that is all. And finally, there are 2 optional questions which are a little bit more difficult, but not so much. So depending on how many answers I get, I will give some chocolates. For the last questions, you can use Mathematica, but you have to follow the instructions which are given. Yeah, you can use Mathematica as your backup equation. Has everybody had Mathematica? No. Okay. All right. So next lesson we will do more Mathematica. I will ask Ramzan to prepare